Okay, so this is the first lesson of our next area of study. Electric circuits is what I've shortened it to. Alright, so it's basically about electricity stuff, some introduction to a few things about that. So first thing we need to look at is electric charge. And so in electric charge, there's a few things we need to know in the notes here. Just going through the whole bunch of dot points there. So the unit of electric charge is the coulomb, after coulomb. And we use a big C for that, big C, not little c. So to get 1 coulomb, what you need there, as it says in your notes, is 6.25 by 10 to the 18 electrons. It says electronic charges, so it's a charge on an electron. So that's how many electrons you need, 6 points, so it's a lot of electrons. So if you go backwards to the other way, so the charge on an electron is 1.60 by 10 to the minus 19 coulomb. Alright, and that there is a quantity that we're going to use quite often. Alright, so the fourth dot point down there then talks about the types of charge. So there's two types of charge. Yep. That's a bit of a mess, that. Let's see if we can write properly. Two types of charge, positive and negative. There are two types of charge. How can things get charged? Well, we can get some static, meaning that it doesn't move, and we can get that when objects are rubbed. And so what you get there is a transfer of electrons. Let's get rid of that. Let's write that again. So we get a transfer of electrons from one thing to the other, and then the thing that the electrons have moved off becomes positive charge than what they've moved to. And you can get that if you get little bits of paper and you rub your pen on your jumper, or you get that, and you can pick up the little bits of paper with the static electricity that doesn't move. Right, so that's that dot point. The next dot point's there, like charges. They repel, and unlike charges will attract. Alright, similar to magnets, like poles repel, unlike poles attract, so similar there. Alright, so the other thing that we need to look at when we get to more is that if the objects or the charges closer together, what that means is that you have a stronger force. Between that. Alright, so there's two types of substances, if you like, and so ones that when charges can move along, second last dot point there, they move along conductors and charges that don't move along they're insulators. Alright, so things that would be conductors are like, wires, copper, that sort of stuff. And insulators, things like glass. Alright, so that's all those dot points there. Don't forget the notes are on the website as well, so if you've missed anything that goes in those gaps, they're all marked in red. Alright, so there's a couple of examples here. So, for example, there it's been stated the charge on a rubber pen would involve many billions of electrons. What is the charge in Coulomb by 10 billion electrons? So let's jump to the next page here. So 10 billion. And negatives. So 10 billion. So 10 billion. Now a billion is a factor of 1,000 bigger than a million. So that's 9 zeros after the 10. So 10 billion electrons times by the charge on an electron, which is 1.6 by 10 to the minus 19 coulomb. And you multiply that together on your calculator and you get 1.6 by 10 to the minus 9 coulomb. So again, it's not very much in terms of charge on coulomb. So you need many, many, many electrons. Okay, so the next one here says school Van de Graaff Generator says that minus, let's go to the next page, is minus 3 microcoulomb. Now you'll see these symbols that are used. So what that saves us doing is power of 10, and micro is 10 to the minus 6. So what that means then is that negative 3 microcoulomb is equal to negative 3 by 10 to the minus 6 coulombs. Now the other thing I need to point out here is this negative. So this negative here is just indicating that it indicates electrons, negatives. So when we're doing this calculation, we're going to leave that out, simply because we want to know the size of the charge, and the negative we know that it's electrons we're talking about. So if we know it's electrons we're talking about, we know that's what we've got. So if we've got a charge of 3 microcoulombs, they're electrons of course, that's what the negative is, so we'll get back to that, of 10 to the minus 6, and we know what the charge, that's the charge we've got, and if we divide that by the charge on any single electron, alright, so because here we're indicated electrons, so we're talking about charge on one electron, 1.9, it's not 1.9 at all, what am I doing? It's 1. Right, tap the right thing here now. There we go. So it's 1.6 by 10 to the minus 19 coulombs. We're dividing those things out. Alright, so when we divide that out, that gives us 1.875 by 10 to the positive 13 electrons. So you can see there on my notes there, I made a mistake there because I wrote the wrong number down there when I did that. Should be 1.6, not the 1.9 that I said, so it's 1.875, not 1.57. Alright, so sorry about that. Alright, so how do we know? How do we know that that's what charge on an electron is? Alright, the last bit of this is what we would call known as Millikan's experiment. And Robert Millikan, now there's a video on YouTube that explains a bit more, gives some good graphics about it. So Millikan, basically what he did is he set up a couple of charged plates. He sprayed some oil in there between those two charged plates, and so we had a drop of oil. So basically then there you've got is the force of gravity, so the weight force that acts down. Alright, so on the that second paragraph there, so these two plates, it talks about it there in your notes, X and Y, the two plates, and a charged battery. So we've got a battery that attaches, and we can change this battery around. So the small spheres there that would just fall down due to gravity. Due to gravity they would fall down, then there would be a little bit of air resistance in there because it's not evacuated, it's just in the air, so it's not in a vacuum. So there's air in there, so there'd be some air resistance. So if we take this battery that's down here, let's put it in red, so there's our battery, and if we did that so that we charge this plate here positive and this one here negative, and what he noticed then was that there was some electric force acting upwards. Now, depending on how strong this was made, that sphere in the middle could move. It might move up, or it might still move down but more slowly, or it might hover so it's not moving up and down. Alright, and if you swap it the other way, you could get the water oil drop going down. Alright, so by doing that, you could make some measurements and things like that. And what he actually found was that the charge on the oil drop was always a multiple. So the charge was always it's a bit ugly looking there. Let's always a multiple of a value. Alright, so when it was always a multiple of a value, so he found that the charge on any particular oil drop was always a multiple of some value. So that n is a whole number. This was the charge on the oil drop. And this here, this number, he said is the charge on an electron. Alright, and of course that E is 1.6 by 10 to the minus 19 kilo. Alright, and so the oil drop then, Millikan said, and this is the last dot point there, or not dot point, the last missing thing, the oil drop got its charge by gaining or losing electrons. Alright, so the last bit there in your notes is Millikan determined the mass of the electron and the charge of the electron. Alright, and there's those values there. So the mass of the electron, 9.1 by 10 to the minus 31 kilograms, and the charge on an electron, E, is of course negative because it's electron, 1.6 by 10 to the minus 19 kilo. Alright, so that's it for that. So don't forget there's that Millikan's oil drop video. Have a look at that video. Explains it a bit better with some animations than what I've just done there. I've just given you a bit of an overview. And so then you've got some text questions that are on page